This video is your tutorial on heuristic PI design with second order systems. Now, we'll remind students, as with all tutorials, that we're assuming they've looked at the previous videos on heuristic design, so they've got some basic background. And the purpose of this video is to give you some tutorial questions you can use to test your understanding. In order for this to be helpful, you should read the questions and then pause the video and attempt an answer before you continue and look at the answer that I have provided. Now, just to remind you of the background, we're using simple feedback loops of this form here. And with the heuristic design, we've said that the PI compensator can be designed roughly like this. So M of S is 1 over G over 0 times 1 plus 1 over ST, where T is usually, I've put here desired, but typically that might match the open loop time constant. There is a warning at the bottom here. For higher order systems, this integral term might be slightly too large, and it's possible that you'll need to reduce the gain a bit to avoid oscillation. First question then. Given this system G of S, design a heuristic PI controller and analyse the expected behaviour using a desired time constant of 50 seconds, and then use MATLAB to check your answers. Now, you should pause at this point because I'm going to go on with the solution. So first of all, let's put in some of the data we need to get the heuristic design. We can see here that G of 0 is going to be essentially 6 over 2, which is 3. We're given that T equals 50, and therefore the heuristic design is going to be M equals a third into 1 plus 1 over 50S. And you can rearrange this, if you want to, as 50 into S plus 0.02, all divided by 150S. So next, I can calculate the closed loop transfer function. So GC equals GM over 1 plus GM. And let's put all these numbers in. It's a bit messy, but just live with it. 6 times 10 to the minus 4 times 50 times S plus 0.02, all divided by, and we're going to get the same term again, 6 times 10 to the minus 4 times 50 times S plus 0.02, and then you're going to get plus 150S into S plus 0.01, S plus 0.02. Now hopefully you'll notice there's a common factor here. I can cross that, that, and that. So there's a common factor throughout. So having eliminated that and then multiplying out, if I circle it, multiplying out this term here to make life a little bit easier, you're going to go at 0.03 divided by 0.03 plus 150S squared plus 1.5S. And that's your closed loop pole polynomial. Now, you won't be able to do this by inspection, but if you calculate the roots of this using a quadratic formula or otherwise, then what you'll get is minus 0.005 plus or minus J 0.013. So what do you notice? 1, it's slower than the open loop, because if you look at that pole, the real part here, minus 0.005, is slower than the poles we had up here, 0.01, 0.02. And you've also got that it's under damped. So a very simple piece of analysis. We've put in the heuristic design and we've said, actually, I don't expect the heuristic design to work particularly well. So what next? Now, you remember, in our guidance, we said for second order, reduce Ki, the integral term. And we said you could choose it to be approximately a half. So if I was to do that, then what I would get is M equals 50 into S plus 0.01 over 150S. And you'll see here the Ki term is half what it was on the previous page. So if I now calculate GC for this, what I'm going to get is going to be 0.03 into s plus 0.01 over 0.03 into s plus 0.01 plus 150 s plus 0.01, s plus 0.02. And again, you'll see there's some simple cancellations that go out here, and therefore the closed loop pole polynomial is going to be 0.03 plus 150 s squared plus 3s. And if you calculate the roots of this one, you'll find the roots are at minus 0.01 plus or minus 0.01 j. So you'll notice they're now similar in magnitude to the open loop, and the damping is better. So in this particular case, the damping is acceptable. Only just, but it should be acceptable. So what we should do next is go to MATLAB and see, does the actual simulation back up what we are saying the expectations have come from our analysis on paper. Right, so first of all, let's enter the system and calculate the closed loop transfer function and the poles with the heuristic. And there, what do you see? You see I've got poles at minus 0.005 and plus or minus j 0.13. So not particularly good. So now we put in the next compensator, which is this heuristic, but reducing the ki to half of it was previously, and calculate the poles in that case. And what do you notice? The poles are a little bit faster and not so badly underdamped. I can now overlay the closed loop responses I get for these two compensators in order to compare them. And what do you see? The basic heuristic gave us quite an oscillatory response. Whether you think that's acceptable is up to you. So a reasonable rise time, but an overshoot of close to 30%. Okay, and not particularly fast settling time. When I reduced the ki to a half, you'll see, okay, I've got a slightly slower rise time, but a much smaller overshoot and a faster settling time. And also, if you look over here at this plot of the input responses, you'll see by reducing that ki, the input is also not gone nearly so large or nearly so oscillatory. So as a general rule, you'd say the heuristic with the integral divided by 2 seems to have given you fairly good behavior. Okay, next question. So here we've got the same sort of thing. We've got a g and we've got a k, and we want you to look at that and say, what do you think? So first, let's calculate our closed loop transfer function, which is gm over 1 plus gm. And I'm going to rewrite this k just for convenience, so we can see as s plus 0.4 over 3s. So what do we get? We're going to get 3s plus 0.4 over 3s plus 0.4 plus 3s into s squared plus 3s plus 1. And the first thing you notice, of course, is there's a common factor of 3 throughout, so we can get rid of all of that. And then we can look at this polynomial here, and you'll see we get s cubed plus 3s squared plus 2s plus 0.4. And you're probably going to say, well, it's not immediately obvious to me whether that's good or bad, because it's a cubic. But what I'm going to do next is I'm going to say, okay, let's compare k of s to the heuristic. So I can't analyze that pole polynomial without actually putting it in MATLAB and finding the roots exactly. But I can do some other things. So if I look at the heuristic, we had that g of 0 equals 3. And if we looked at the poles of g of 0, you'll see that s squared plus 3s plus 1 is approximately s plus 2.6, s plus 0.4, and you notice I'm emphasizing that's approximate because that's good enough. Now this is very overdamped. you'll see you've got two real roots, and they're quite widely spaced. And therefore I'm going to take the slowest and say that t is therefore going to be approximately 1 over 0.4, which is 2.5. So I use that for the heuristic. Then what I'm going to get is k of s equals a third, that's 1 of g of 0, into 1 plus 1 over st, which is 1 over 2.5s, which gives me a third, into 1 plus 0.4 over s. And what you notice, it's the same as we gave you. So we'd actually given you the heuristic compensator. So the question is now, is that likely to be a good compensator? Now I'm going to point you to the bottom left hand of this screen. What did we notice down here? The system is very overdamped, and that means it can be approximated by first order with slow mode. So in this particular case, the heuristic should give us a good answer, because the second order system can be approximated by a first order system with the slow mode. So let's go to MATLAB and see if that's the case. Has the heuristic worked for us? Okay. So first of all, we enter in the system. There's g and k. We calculate the transfer function. There's gc, and we look at the poles. And there you go. You've got poles at -2, that's a fast one, and you'll see poles at -0.42, plus and minus a relatively small complex bit, so it's pretty close to critically damped. Now what I'm going to do is also add the compensator with this typical second order guidance, where you treat the integral as being half of what you get for first order system. So you'll see k2 has got this 0.2 here, whereas the original k we had 0.4. So we've halved the integral, because that's what you said the guidance was for second order systems. Now, let's run the simulation and see what happens with both these compensators. So with the heuristic design, we have this blue plot, which is smooth, goes to the steady state, quite a good time constant, and there you can see the input. Okay, it overshoots a bit, but not enormously, given the steady state of a third. It's gone up to about 0.38. Now, when we halve the integral term, you get this green plot. Do you notice it's much slower, and the input undershoots rather than overshoots? So what's the key point here? The heuristic has actually worked very well here. We haven't had to reduce the integral term. And why is that? So we'll revert you back to this box down here. This second order system is very overdamped, and therefore you can approximate it by a first order system, and therefore the heuristic is likely to be a good controller. Right, third question. What have we got here then? So you're given a compensator and a system, so let's investigate these. So again, what I'll do with this k before I continue is rewrite it in a form which might be slightly more helpful. 60s plus 3 over 20s. So let's work out what gc is. So you're going to get 4 into 60s plus 3 over 4 into 60s plus 3 plus 20s into s squared plus s plus 2. So now, if I look at this pole polynomial and see what I get, you're going to get 20s cubed plus 20s squared plus 280s plus 12. So again, what do we say? It's difficult to assess, on paper, because you can't see where the roots are. So we'll do our normal trick and we say, okay, let's see what the heuristic design would give us, and then give some comments. So if we did the heuristic design, we would get g of 0 equals 2, and the time constant, t, now that might not be obvious, so how are we going to get the time constant? So let's put a little balloon down here and look at the open loop. So s squared plus s plus 2 can be written as s plus a half squared plus 1.75, and that tells you that the open loop time constant is 2. It's an inverse of the half. So I've got t equals 2. I can now use these two values, and that's going to give me the heuristic is going to be 1 over 2, that's 1 over g0, plus into 1 plus 1 over 2s. Or, putting it in a slightly alternative form, s plus 0.5 over 2s. Now you will see this is very, very different from the other compensator, which if I put it down, if I divide what we had 3 plus 3 over 20s, and you can see they really are quite different. So for one you had kp equals a half, for the other you had kp equals 3. For one you had kp equals a quarter, and for the other you had kp equals 3 over 20. So you've got different comparisons here. If you look at kp, you'll see that the one we've given, kp was too big. We had 3 as opposed to a half. However, if you look at the ki's, you'll see it was too small. So we're going to have an interesting message here. What's that going to lead us to expect? So we've got kp too big, ki too small. And the other thing you might want to look at is you had an oscillatory open loop. Okay, so that's going to change things as well, because if the open loop's oscillatory, you might need to reduce the gain on the compensator slightly to avoid getting too much oscillation. So let's have a look now with MATLAB and see what we get. So we go down, so I enter my G and these two compensators, the one given and the heuristic. Calculate the closed loop transfer functions, and let's look at the poles. So what do you notice? With the compensator given, poles at minus 0.47, plus or minus j 3.7, very, very oscillatory, and also a very slow mode. And that might not be surprising, because you'll notice we said the ki term was too small, and the integral tells you about settling time. The kp was too big, and that might explain this rapid oscillation. With the heuristic, you can see that the oscillation isn't quite so bad. It's still bad, but not quite so bad. But critically, this slow mode is faster than with the other one. So let's overlay them, the responses, and see what we've actually got. And there you can see it is a bit of a mess. It doesn't look nice, but the compensator given, you can see very oscillatory, up and down this blue curve, but also can you see very slow to settle. If you look at the heuristic, which is the green one, still oscillatory, not as bad, but settles much, much faster. The key thing is, neither of these are any good, but the heuristic's better than the other one, and it's given an indicator of where to start. Still a bit too oscillatory, so what am I going to do? I'm going to suggest, as you'll see in this command here, that we basically reduce the gain by half. Can you see I've put the heuristic compensator, but multiplied it by a half. And what does that give us? So I went to the wrong window there. And you'll see by doing that, the decay rate is okay. It settles just a little bit slower, but can you see it doesn't oscillate as much? And if you look at the input, you can see it's a lot smoother. It's not oscillating so much. And so the heuristic has given us a good place to start. I could look at going somewhere in the middle. So with this command, I've multiplied the heuristic by 0.7, and now I get that red plot, which you can see the oscillation is somewhere between the two, the settling time is somewhere between the two. But the key thing is, in terms of PI, you're never going to get an excellent response for this system because it's very underdamped in the open loop. But the heuristic has given you an indicator of where you might start. So in conclusions, we're given some tutorial questions with second order systems and analysing the heuristic PI design and how it might help us. But students are reminded this heuristic is not an ideal solution. It's an indicator of where you would expect your PI parameters to be, so that if you're a long way out, you should be able to spot it.